So we are talking today about functional reactive hard real-time Erlang programming. So you probably heard about functional reactive programming, and you heard about Erlang maybe, and you heard about hard real-time, and you know that Erlang is soft real-time. So there's a discrepancy here, and we are talking about this today. So that's me, and that's Kilian, who basically built the demo and did a lot of the code of the talk, and will do half of the talk, but I think I'm going to start. So why do we want hard real-time in Erlang? So we kind of build these embedded systems and use Erlang in embedded systems because like Erlang much, and if you use Erlang in an embedded system, that's very useful because you have a lot of properties in Erlang that are very helpful to build embedded systems, especially networked embedded systems. And so this system that you see here, that's a little controller node, and basically the actual board is just in the upper part, the lower part is just cabling, so it's actually smaller. That's a factory demonstrator for Bosch, where they do transport systems, so they do conveyor belts. I brought you a little video. Does this run? Nope. Yeah, there should be a video. So this is a conveyor belt system. It's moving? Oh. Oh, only you see it. I don't see it here. This is a conveyor belt system, like a medium-sized thing. So you have these little pallets running around, and you have RFID tags on the pallets. I don't know when you see the RFID tag now. Basically, you identify the product, and then you decide what to do and to move it to a different direction or to actually stop and work on it. These conveyor belt systems are huge, like spanning a whole factory, and kind of the natural way of actually controlling those things, the movement of the whole parts, and also the RFID system is in a distributed system manner because the best way from the cabling and from everything else, and also from the price point, is to have lots of little nodes close to the locations, sharing sensors, do a distributed system with this. And this actually, what you saw here, was controlled by 15 little Erlang nodes running on a little board, a little embedded board. So this is basically how this started, and that's the motivation for doing hard real-time things, because these conveyor belt systems, there are certain movements need to be in time. I mean, there are some movements that if you're late, it's only slow, but certain things need to be in time, or otherwise the pallet falls off the thing, so bad things happen. So it goes beyond the end of the conveyor belt because you didn't stop it or whatever, or it crashes into another pallet or whatever. Several bad things happen if you're not in time. And Erlang's soft real-time kind of is almost good enough, but not for all the applications. So this was just with a standard Erlang system running on a hard real-time operating system, which makes it already more hard real-time than it is if it's run on Linux, on the Raspberry Pi, because the Linux basically preempts your Erlang system, and then you're not getting anywhere. So the way of the kind of hard real-time that we have here, that's actually I'm behind with my slides. So the kind of hard real-time that we get here is kind of event-based. It's not like a closed control loop, which we do periodically, very quickly, things to control something. We could do that too, but the application space we have is a certain event happens, which we detect by a sensor, like something comes by, and we want to stop it in time and not fall off the conveyor belt. And so in order to get towards hard real-time in Erlang, the first thing, as I mentioned, is you need a hard real-time operating system, because if the operating system messes with your hard real-timeness, then nothing is gained. So what we did, like a few years in the past, we ported Erlang to Artem's operating system, which is a hard real-time operating system. We will be talking later about this. So this is all running on this stack. So that's basically how this looks in the inside. We have the Erlang code that basically runs in the Erlang runtime, the VM, and the little box below with the blue things in, that's the actual Artem's operating system, but it's an operating system with quotes. We also get to that because it's just linked, it's a very thin layer between, hello? Oh. between Erlang and the hardware. So the hardware is below, and we can use NIFs and port drivers to directly talk to the hardware. So hardware is accessible, like hardware registers are accessible in a NIF or port driver to the Erlang code. So we can write very thin layers of C code to actually get to the hardware. A little bit like explanation, like what's actually soft real-time and hard real-time. There's lots of definitions, and there's also firm real-time and all kinds of real-time. If you look at like an event-based system that like you get a starting event, and then you need to do some processing, and to be done with your processing and have your actions happening at a certain deadline. So everything has a certain deadline where you need to be done. If it's a soft real-time system, both basically have the average execution time, which is lower than the deadline. But a soft real-time system can occasionally get above the deadline, rarely. And that's not like a bad thing. Like the system value basically drops like continuously when you go. It drops pretty fast if you say anything real-time. It's not like, yeah, okay, you can slow down until the user gets bored and goes away or whatever. So that's not what soft real-time means. It's a normal system, a non-real-time system. But it's very rarely going over the deadline. But the hard real-time system never goes over the deadline. So going over the deadline is actually a failure. How would you want to achieve this in a functional dynamic language like Erlang, with garbage collection and all these little obstacles to hard real-timeness? So garbage collection is a problem because it can happen at like arbitrary times and actually mess with your timing. Erlang is pretty good at that because its garbage collection is only per process, so I have little heaps that gets garbage collected per process, and actually other processes can do some processing while the garbage collection in one process happens. So it's not that the system stands still. But if you are in this one process which actually wants to react in time, then you actually want to avoid an arbitrary long garbage collection. So either you want to have some real-timeness in the garbage collector, so a different kind of garbage collector, they exist, or you want to basically get the garbage collection out of the way. And so the way that we actually conceive this is that if you do an event-based system, the scheduling is deadline-based. So, and we added an additional deadline. So we have two deadlines. One deadline, so the green bar is basically our processing time. So before the green bar, we get an event, like a message, because Erlang is message-based. We get an event like a message, and in the green area, we need to do all our processing and all our actions to the outside world. Send all the messages, set the hardware, turn the motor on, whatever, or turn it off, do not fall off. And in the blue area, basically, this is our recovery time. So this is the time until we are actually able to process the next message. And usually event-based systems have pretty decent recovery times. So the recovery time is usually much longer than the actual action time. So you want a very quick reaction to an event, but the events don't happen that often. So for example, if you have these little pallets coming by, the next pallet will not be showing up in a millisecond because it's not physically possible that it already is there when the one just left. So if you look at the second deadline, what you define by that is kind of a maximum message rate that the process can take. Because like the second deadline is the period of the maximum message rate. And that's actually a useful design parameter if you design a system, because you can actually throttle the maximum message rate if you have some inputs, or you actually make sure that you don't overdo this. And the green one is basically the reaction time, the reaction deadline. And what we do is we put the garbage collection in the blue area. So once we're done doing processing, we always do a garbage collection. And we can use the normal garbage collector then. And the garbage collector needs to be done by the end of the last deadline. And since basically the processing in a hard real-time system is kind of limited, and you know that you use a limited amount of heap, this garbage collection actually is also bounded because it's always the same. Every round you go around your loop, you produce the same variables and you do the same kind of garbage collection. So this is not the fastest way to do things, like the best throughput thing, but there's a discrepancy. If you do a hard real-time system, you never go for throughput. You go for real-timeness. You cannot have both usually. It's very hard to do both, high throughput and hard real time. So that's how it would look like if you have like two processes, like the two lines of two processes, being scheduled by an earliest deadline first scheduler, which is one of the ways hard real time gets scheduled, which is very fitting for this use case. So basically, it sorts all the processes to whoever has the next deadline and runs the process with the highest priority that has the next deadline. So it's the longer deadline, so the green area in the second process can actually interrupt the blue area in the first because hello, 1, 2? Because the deadline is longer. So yeah, that's how it would look like from the scheduling. So what we in addition want to avoid is actually that Erlang is actually getting a new heap, like because the memory allocator of the operating system might have unbounded time. It's not bounded. It needs to search for a right-sized memory. So what we're planning to do in the Erlang VM. So this is all things we want to actually add to the Erlang VM, I have to say. We pre-allocate the heaps. You can do this now. You can basically tell a process in the beginning when it starts, like, yes, let's start with a heap this size. And to avoid getting any memory allocation thing, we basically pre-allocate another heap. So we have a dual heap thing, and we do garbage collection. The garbage collector is a copying one, so it needs basically two memory areas, where one it copies from and one it copies to. And we basically always copy from one heap to the other, and then back again and to the other, so we never need a new heap area. And we also probably want to limit the message mailbox either by system design, that we actually make sure that there is no more than a certain number of messages in the mailbox, because message mailbox size is also getting like variable timing in there. And we, by doing that, we can actually use the normal garbage collector. And then the question is, what do we actually do when something doesn't work? Because it's always a probability that some bad things happen on your systems and you miss your deadline. And since in a hard real-time system, actually this means probably that your state is kind of corrupted, which makes you kind of take too long for processing and miss your deadline. So this is an error, like the usual let it crash error or let it fail error of Erlang. So we let it crash too, and take care of the supervisor to actually restart the subsystem. So we have a glitch in the system that it actually is not working for a short time, but then it will recover by itself. So we can get the failure tolerance together with hard real-time. And there's actually maybe an area for useful research, how you can basically combine failure tolerance with hard real-time things. There's also an optional quick auto restart on a crash. So since we have pre-allocated all the heaps and know everything about it, we could actually not go to the supervisor to restart the process, but we can just clear the heaps and jump to the beginning and do a very quick auto restart, which is much faster than the supervisor would do it, and then have a count on it. And if you do it too much, then the supervisor jumps in anyway. So what do we do on message overflow? There's basically 4 possibilities. We can crash the sender because it sends too much. We can crash the receiver because it's too slow eating up the messages. Or we can actually drop messages. And there's also 2 things: drop the old message that's already in the mailbox, or drop the new message that's not in the mailbox, that just came in. For example, if I have a new temperature reading, I don't care about the last temperature reading anymore. I just drop it. I work with the latest sensor reading, so that would be drop the old one. So that's a little bit of the inside, how we are actually planning to implement this and how this actually looks, because there's nifty little details about how the I/O systems work, how the drivers work, and how the NIFs work. And we also need some help there in addition, because we have the normal Erlang scheduler, and then we have an additional Erlang scheduler or a group of scheduler in case of an SMP system, which runs on a higher hard real-time operating system priority. So the hard real-time Erlang scheduler always preempts the other one. It's basically, it looks like a scheduler on a second core, except it's on the same core, but always interrupts the other one. So it's always getting priority. To talk to the hardware, to actually write something to the hardware, you can still use normal NIFs, because you go into the NIF, you write to a register, and it gets maybe even a value, read something from a register, and you get the value back. This is bounded time. This is not a problem. The problem occurs when you need to wait for something. So if you wait for something like the traditional way would to do, like asynchronous I/O, is this basically wait for I/O to happen or an event to happen? The traditional way was using a port driver for this, which then goes through the operating system select call, which is basically the way the Erlang VM, there's other calls, but this is the basic one, and the one we use in Atoms, which is a way for the Erlang VM to wait for multiple things to happen on multiple file descriptors. So you need a kind of a pipe or something, or you need some file descriptor, and you need to wait on the file descriptor there. And then the Erlang VM actually notices that something happened and actually sends a message to the process who is actually watching the port. As of recently, you can also use this with NIF. So they added a functionality to make this select thing available to NIF. But the problem is that we don't really know what kind of like operating system machinery is behind the select call and if it's hard real time. And also, we need to make sure that the routing of the select file descriptors go to the right Erlang process, and there's some kind of shady area here. The best way to go, so the select thing is fixable, but that might not be the nicest way to do it. The nicest way to do it basically on the overall timeline of actually improving native implemented function, NIF functionality, is native implemented processes. So it's basically on the roadmap of OTP, so maybe we implement it or we wait for them to implement them. That's basically a process that you can write in C, for example, which runs in a separate thread and which can actually send messages at arbitrary times to arbitrary Erlang processes. So it basically behaves like an Erlang process, but it's outside of the VM. And with that, we could actually perfectly react to outside events to happen. So I need to speed up a little bit. Okay.
Okay. I built a small scheduler for hard real-time Erlang. I used Erlang only, so it's more like a prototype implementation to see potential and possible weaknesses of the whole approach. I use a shared ETS table for synchronizing the scheduler data across the real-time processes. ETS has the advantage that it's very fast and you have short tables anyway, and it's very optimized. So it's the best way to do it, I think. And the type of scheduler I used was a cooperative earliest deadline first scheduler. The issue is that you can preempt other processes in Erlang, so you would have to go to the VM, and, which does this usually. So I have to rely on some collaboration between those real-time processes. Actually, it's more of a hack. I will go into it deeper in the next slide. And there can be things going wrong. So I implemented also a Watchdog, which will take care to clean up the ETS tables if something crashed, for example, or a process missed a deadline. So in ETS you have 4 fixed priorities. It's normal and low, where you usually have your normal soft real-time processes running. And there's also high and max, which you actually shouldn't use, but I did nonetheless. And the trick is to have all real-time processes waiting in the max priority. They are in a receive, so they are blocked because they don't get a message. As soon a message arrives, the process will call the scheduling algorithm, and then it will be decided if it can run. If it can run, it will go to the high priority, and it will start its task. If another process receives a message, it's still in max and can preempt the other one. But yeah, it's a hack. It's not perfect, but it works quite well. Yeah. Okay. We are talking about real-time software mostly. So what about the hardware and about the operating system? We have a small board available. It's called Trisport. I will go into detail it. You can order it already, and I will present it to you. You can also build some cool stuff with it. This is it. It's looked like this. It's manufactured in Germany, and it has Wi-Fi on it, so you can build cool Internet of Things application with it. Erlang is running closely to the CPU without much operating system interference. So you can all have that if you want to. There are many connectors for sensors and actuators. I will show it what we have later. It's a 300 megahertz CPU. We have 64 megabyte of RAM, which is enough to start the VM and to run most applications. We have the Wi-Fi, and we have a micro SD card slot for the actual program. This is the CPU. It's an ARM Cortex M7. We have a floating point unit and a DSP unit, which we plan to make available from the Erlang side. So you just have an Erlang module and can do digital signal processing in hardware. And we have internal of 2 megabytes of flash, which is used for the bootloader, and 300 kilobyte of RAM additionally, which we don't use yet, but we plan to make things faster. There's a micro SD slot, the Wi-Fi, the GPIO ports, which also support pulse width modulation. We have 2 of them. We have RGB LEDs. We have little switches, which you can access from Erlang. We have a reset button to reboot everything. We have a UART port and 2 SPI interfaces. You also have some interrupts, and you can have multiple SPI slaves. There's an I2C bus also. The next talk of Claudia and Adam will go more into deep with this. Also a one-wire bus. There's also a demonstration about that in the next talk, so if you're interested, just stay. We have a micro USB slot, a micro USB port, which is used for the power supply of the board, and you have a serial console, and you have also a GDB OpenOCD debugger, so you can debug C code on the hardware. And you also can use an external hardware JTAG debugger.
So I think the Pmodes are my thing. So the connectors you saw before, they are actually conforming to some standard by Digiland. It's called Pmodes. And you get lots of little, lots means like over 100 different sensor and actuator boards, actually quite cheaply, and you can just plug them into these Pmodes. There are different kinds of Pmodes. That's the different SPI, UART, GPIO interfaces. Which means, and we are actually providing drivers on the Erlang level for lots of these Pmodes, and the most usual. And this means that basically you can build all kinds of things with the board. You're not limited by the board. You just plug in the Pmodes that you need, and then you can build almost arbitrary things. So let me go through a few Pmodes to show you what kind of things are actually available. This is a Pmode that makes it possible to connect 4 servo motors, like just the standard servo motors for model planes or something. You can connect 4 of them to 1 port. The Pmode nav is a Pmode that is pretty cool. That has a 10 degrees of freedom navigational thing. So you get like 3-axis accelerometer, you get 3-axis gyro, you get a 3-axis magnetometer, like a compass, and you get an air pressure thing to actually have a height measurement. So it's precise to actually know that if you're a few meters up. And the air pressure sensor and the temperature sensor for good measure in addition. So it's actually 11 degrees of freedom even in one Pmode. There's also like all the Pmodes which just implement the 3-axis gyro or just an accelerometer, but I would recommend just go for the Pmode nav because we have a very extensive driver for that, and it just has everything you would ever want to about like inertial measurements and location things. There's basically lots of different motor driver things. That's the H-bridge Pmodes, so you can actually wire up a higher powered motor to it. So you can basically run the motor forward, backward, and with pulse width modulation you can actually modulate the speed. Very thing, you see, the motor just, gets a standard plug into the Pmode and you're done. So we actually have a robot, but the robot is actually in Berlin at another conference, a robot that drives around. There we use these motor drivers. And there's also like a Pmode for GPS. So for example, if you're outdoors with a drone, all you need is the Pmode nav and the GPS Pmode, and you always know where you are very precisely. You just need to do a little bit of filtering and nifty processing. Sorry. The Pmodes are actually, the interfaces to the Pmodes are actually pretty simple, and it's an ideal first way to do your first own hardware thing. And here you see one that actually built up. That's the one that's actually running the demo. So that's just a breadboard, and we just soldered a few boards on it. We will hear about them later. So you can basically very easily make your own Pmodes as a like beginners soldering project things. Software is Kilian again.
Okay. So we were talking about hardware. Now I will proceed with the software stack, which is running on this board, which is actually very similar to the one you've seen in the video, just a little bit other hardware. We use, as Pierre already mentioned, RTEMs. It's a real-time executive for multiprocessor systems. It's open source and free, and it's you don't have any processes there, it's just threads, so everything is shared. You have no memory protection, but you have a full POSIX-compliant API, which you can use, and we do use it for the ERTS. We have SMP support in the board, also a networking stack that comes from FreeBSD, and everything is statically linked, so there is no dynamic code loading, everything is statically linked. The GRiSP runtime is the thing above that. It's basically an Erlang application which has many linked-in drivers already. So all for the basic connectors, everything is done. You can just write device drivers purely in Erlang. It's very cool. You're very fast. It takes not much effort. You don't have to stick with registers and bit shifts. You can just use Erlang binary pattern matching and stuff like that. It's very powerful and very easy to write new drivers on top of the existing drivers. The hardware is abstracted, of course, by that, and yeah, we have drivers for almost the basic stuff is done. The tooling makes it very easy to deploy your own application. We have created a Rebar 3 plugin. There's a template which you can just use by calling Rebar 3 new GRiSP app. It will build a directory structure for you, everything you need. And it will place your Erlang files in there, and you can then build the application with Rebar 3 GRiSP build. And this will link the, this will first compile, cross-compile the ERTS runnable to the GRiSP hardware, and also link against the RTEMS operating system. And then finally you can deploy it on the SD card.
I think it's my turn again, while Kilian actually takes care of the demo and makes it run. So, in the demo, I explained the demo a little bit. We have a stepper motor here. And I explained what stepper motors actually are. And we have a little pipe, and we have sensors. And we have this board that I showed you before. So let's maybe explain what's a stepper motor and what's the difference to a normal motor. So before we saw this H-bridge where you can go forward and backward, and you can kind of like do some speed control loop, but that's actually a lot of work. A stepper motor actually has a lot of nice advantages. It has very exact positioning, so you basically tell it, go to this angle, go to this position angle, go this 30-degree forward, or like go 10 turns and stop at this exact position there. So that's why it's used in printers, in 3D printers, for example. 3D printers all run on stepper motors. That's basically, there's no question if you have a stepper motor or not. They all have stepper motors to actually for the positioning of the whole thing. You can also control the speed very well because it depends on the actual, like you basically tell it like increase the angle by this rate in this time, so you can actually very precisely control speed. And if you do two stepper motors, that actually you control with the same way, they would actually run synchronously. So how do you actually achieve this? Maybe I explain the picture a little bit. So you have lots of coils in there and magnets, and the way you drive it is not like that you basically do a turning field and then it goes around, but you always basically apply force to the next magnet, and like you pull it to the next magnet and push it away from the old magnet, and so it goes to a discrete position. And normal stepper motors have lots of these discrete positions where they can actually position them. So for example, this one has like 200 positions going one time around. So it's 1.8 degrees, one position. And the controller can actually, by actually driving the current to two coils, basically slowly, like a little bit of this, like 10% of this coil and 90% of this coil, you can have sub-steps, which means you can have 256 sub-steps between this 1.8 degree, which is very, very small steps and very precise. They're also very cheap because there's not much in them. There's not much moving parts. There's nothing that actually kind of wears down because there's just these coils and magnets, and that's it. There's no, you don't have any force, any current into like a moving part, like with some things that then wear down and you need to replace them. And they also have pretty high torque, but they also have disadvantages. The disadvantage is that if you go step by step, basically, you dump the same energy for every step into the stepper motor. And if it kind of behaves weirdly, because if it's unloaded, if it doesn't have anything to pull, then it actually gets pretty hot because it needs to get rid of the energy, which is also a waste of energy, of course. It's not energy efficient. They can be noisy because this stepping kind of like makes a piping noise, like this of old printers. That's actually the stepper motor you hear. Also, if it's overloaded, you can actually skip steps. So it doesn't fail well because it either can go to the next step or it can't, and then it just skips the step, and then you don't know where you are anymore. Fortunately, there are controllers which are very, very smart and control the current while the step actually happens. So it measures the current, how much goes into the coils, and can therefore deduce how much the load is, and stops the step early, basically, when it's actually already there. So it knows when it took the step successfully, so it actually can take off the load. And the advantage is you take away all the disadvantages. So you get all the advantages and take away all the disadvantages, and then the stepper motors are actually perfectly usable for almost everything, except going very fast. It also, you have motion planning. So these controllers have a high-level mode. You basically tell it like, accelerate in this rate to this speed, then go on this speed until this position, and right in time to start to decelerate to stay at the point. So you can do very interesting things without a lot of like closed controlling. So you can control them step by step, but you can also do it in a like a higher level way. So that's very suitable for Erlang. So the demo is running already. What we have in the demo, actually I think I switch over to you and show the demo on the video, like earlier. So you explain the interrupt driver and the demo, or I explain the demo and you the interrupt driver, or whatever. Okay. But actually it doesn't work, we need the slide. Nice try.
Yes, we are using an interrupt driver, so pin interrupt is something where you can configure the CPU to jump to a special routine you can configure. So this is running purely on hardware. And we have this sensors actually connected to pins we've configured for an interrupt. And
I think I go to camera.
The goal is to have this interrupt events as Erlang messages. So I wrote the interrupt driver in C for the GRiSP runtime. You can use it soon. It's soon also on GitHub. There needs to be some trick because you can't just send a message out of nowhere in Erlang. And also you have to take care what to do in an interrupt service routine. That's how the callback for an interrupt is called. You have to send a message to another thread and then use a pipe, and then this pipe goes in a select, and the select will eventually send a message.
I think we move forward with the demo. We're running out of time. Mm-hmm. So what you see here is a plastic pipe and a little metal ball running around the plastic pipe. Can you see the ball? Is it visible? Okay. So it goes around. So the pipe is open at the ends. So if you basically don't tilt the pipe in time, we would lose the ball. And to actually know where the ball is in a little way, we have these sensors here. That's actually inductive sensors, so they actually detect the presence of metal, and the ball is made of metal. So, and if you look at them closely, you see when the ball goes through, the little light flashes on the sensor. And that's actually what hooks up to the interrupt driver Kilian was actually explaining now. And then we need to react in time. And what we want to show in the demo is that actually Erlang, with the little tweaking we did already, is already fast enough to actually not lose the ball here. So that's actually pretty close to the manufacturing application because you don't want to lose the pallet over the end of the conveyor belt. So the ball is basically playing pallet here. So you see here, that's the picture I showed before, that's the GRiSP board with the wired stepper controller here. So that's the stepper controller. And that's basically some resistors to basically get the voltage of the sensors down. And that's the stepper motor. And you see, it just keeps going. It's very mesmerizing. I could look at it for like hours. But let's go on. So we keep it running so you can see that actually it doesn't lose the ball. So next slide. That's the demo. So that's you again.
We have some interesting updates. We are shipping since November, and we are still shipping, so you are free to buy one. We'll be happy if you buy one. We will do the software release 1.1 this month, and we have now WPA2 running, so you can have encrypted Wi-Fi. We upgraded the Erlang to the latest version. It's 20.2. All basic drivers are done, so you're ready to go basically and start your own projects.
Oh, that's brilliant. Okay. So we're also using the GRiSP board in the Lightcone EU project. It's about Internet of Things and edge computing with Internet of Things. So edge computing means you push the computation to the edge, away from the data centers, because the data centers can't keep with Internet of Things growth rates, expected growth rates of devices. And we use it basically for the Internet of Things application. It's very convenient there because we can actually, lots of the researchers are using Erlang code for their distributed systems models. And now we have a board where we can basically run the same code that we actually run in the server also in the board, so you can actually decide where you want to run the actual code. The roadmap in the future, more drivers, a pre-built cross OTP is basically will be showing up next week. That means that you don't need to build the toolchain anymore, makes it even quicker to get started with the board. And we're also working on fixing Erlang distribution in this research project to make it more scalable, like the Erlang distribution protocol has scalability problems. So we're kind of running out of time, but we have one topic untouched. That's the functional reactive programming thing from the title. So let me rush you through this. So the general thing is like, usually Erlang programmers, when they hear about like Haskell programmers doing functional reactive programming or wherever, we basically say, yeah, but do we need that? I mean, kind of like we have this message passing and it's asynchronicity, and so really in Erlang, it's kind of like a non-topic there. But still you can, especially for these hard real-time systems, you can improve it. So that's actually how Erlang works now. You have encapsulated processes which only communicate via messages, and normally, if you have like if you do it the OTP way, you encapsulate the message passing part, which is the non-functional part, because messages are a side effect, the classical side effect. If you send a message or receive a message, that's a side effect. That's not pure functional anymore. And you separate basically the side effect code into so-called behaviors, and have your functional code in pure functional callback modules, where you then basically write your application code there. So there's a separation of concern, and you have functional and non-functional. There's especially for these like controls things, a more higher level way to actually look at this system is actually you have like modules that do some processing and react to events, and they're usually connected by a flow graph, which then basically is wired up, and the messages flow from one, or the event, the abstract event goes from one block to the next. So you have building blocks, and you can actually assemble them to larger systems. And if you look at a system at a flow graph of a system, then you actually can reason more about the system, because then you, for example, if you want to know the deadline between the two yellow arrows going in the system and out of the system, that's very useful if you actually know where all the messages go. And traditionally in Erlang, you don't know this because, well, you just have processes and you don't have a statically accessible way of actually this graph looks. So what we actually want to build, or actually partially build, is a way to actually specify a flow graph over kind of like real-time modules, which will be special behaviors doing this. And then you can also do things like, for example, if you look at this flow graph and you do all this with messages and you have like a long flow graph, that might be good for throughput, especially in a multi-core system, because you split up your computational things over multiple cores. But if you want to reduce latency, that's actually bad because you have lots of messages and lots of switches of context, so you're actually increasing latency by using lots of processes. By having this flow graph and encapsulating the functionality in functional modules, we can actually group them together when we don't need messages. So we can actually call just functions along a chain, and then when it gets too messy for us, we fall back to messages, and we reduce the latency by this. And we can do this automatic at system startup, for example. So this is a little bit complicated. I just hand-wave me to myself through the slides because no time. The way we actually do this, that's two of those blocks, and these blocks have like plugs, which have names. That's the green things, that's plugs, where you can actually plug them together with these arrows. And that's basically a standard two blocks of a protocol stack where you have up and down. You have basically a downwards thing, and you might have a shared state in every level, and going back up. And the way we actually connect these, when we don't want to have a message passing, so we can have, if message passing, it's trivial. But if you don't want to have message passing, we actually, at system startup, when we basically start the subsystem, we pass around, basically, we wrap the static configuration, or the kind of dynamics, like runtime static configuration at start time. We wrap it into a closure, and we pass closures from one module to the next, wrapping all these things. And so basically, what you at the end, in the first process of a chain, you have all these wrapped closures, and can call this functionally without any process switches and without any message passing. So that's the way we are doing this. We're actually using this in the protocol stacks for this Hydroproc device, which has to implement a lot of automotive protocol stacks in a flexible way. So that's why we try to get a more higher level approach to actually plug these Lego blocks together. And so that works very well, and we also want to use the same technology for hard real-time things to make it more functional reactive programming. And that gives me to the last slide. Well, yeah, the GRiSP is available. We can ship. There is actually a discount during Lambda days until Sunday. If you enter the code Lambda 2018, that's on the slide, and it's also on the poster outside, you get a 20% discount on all your orders. So get some boards. We need to get rid of them. So we can build new boards. And the price drops when you buy lots of boards, because the price of manufacturing is basically about like the piece count. And by that we are done. And we have 2 minutes for question, or 1 minute. Microphone. Kannst du ein Mikro? Ah, er hat ein Mikro. Okay.
I saw Adam Lindbergh's presentation at EFL in Berlin, like 2 years ago, and thought, oh, cool, I can try that now with Erlang. But then I saw the price, so for just playing around, it was quite high. So can you, I
can explain the price.
No, it's not about the price. It was just an opener. So is there a certain area of things where you would use this instead of just taking a Raspberry and put Linux and Erlang on it?
Well, so you do very different things with it. You can do things that you can't do with a Raspberry Pi.
Yes, of course. But
and it's much easier to actually get started on the Erlang level because we provide all the drivers than with a Raspberry Pi, where you actually, I mean, there's like Nerf's project, and the constant complaint I hear about this is the lack of drivers. And we basically fixed this by building our own hardware, because the problem with the drivers, these are a lot of work, and if you basically pick a BeagleBone or Raspberry Pi and write the drivers for this board, by the time you're done, they make a new board, and then you say, oh, we have to start again. So having our own hardware, we actually can control when there will be a new board, and we actually can pick the new board in a way that we actually can save effort writing drivers. I know the price point is quite high, but if you're looking at academic use, please talk to us. We will be sponsoring some academic projects if they look interesting. And it's also meant for professional development. We use this for prototyping our devices and our products for our customers. And for that, it's actually not expensive.
Thank you.